Our perceptual systems take in an astonishing amount of information about the world around us, but have limited resources to store this information into memory. In this paper, we explored whether auditory perceptual representations could be explained in part by such memory constraints. We focused on representations of pitch, the perceptual property that enables sounds to be ordered from low to high. Pitch is an important feature of music, speech, and many environmental sounds. Sounds said to have pitch are typically harmonic and contain frequency components that are integer multiples of a common fundamental frequency, or F0. We wondered whether the F0 might provide a compressed representation that would be particularly important for memory. We studied this issue by measuring the effects of time delays on the ability to judge which of two tones was higher. We compared performance for harmonic tones, which can be summarized with their F0, to that for inharmonic tones, whose frequencies were perturbed to be inconsistent with any single F0. In our first experiment, we examined pitch discrimination with instrument tones that were resynthesized to be either harmonic or inharmonic. Performance for harmonic and inharmonic notes was comparable when notes were presented back to back. Here is an example of a harmonic trial, where the second note is higher in pitch than the first note. And here is an example of an inharmonic trial. You should again be able to hear that the second note is higher than the first. But with an added 5 or 10 second delay between notes, performance with inharmonic tones was worse than that with harmonic tones. Here is an example of this effect. You will first hear a trial where the tones are harmonic and are separated by 5 seconds. The second tone is higher than the first. Now, you will hear an example where the tones are inharmonic and again are separated by 5 seconds, and again, the second note is higher than the first. You should notice how the inharmonic tones are harder to remember. We replicated this effect with synthetic tones and added a stimulus condition, which we called the interleaved harmonic condition, where each of the two tones in a trial contained only half of the frequency components. While for the harmonic and inharmonic conditions, listeners could use the spectrum, specifically the correspondence of the individual harmonics, to compare the tones, in this new condition, listeners were forced to rely on estimating and comparing the F0s. Performance without a delay was worse for interleaved harmonic tones than for the regular harmonic and inharmonic tones, but unlike in those other two conditions, interleaved harmonic performance did not deteriorate significantly over time. These results are consistent with the idea that a sound spectrum mediates pitch discrimination over short time intervals, but comparisons across delays appear to rely on representations of the F0. This produces better performance for harmonic than inharmonic sounds. In our final experiment, we measured pitch discrimination thresholds for harmonic, inharmonic, and interleaved harmonic tones, both with and without a delay. We measured correlations across participants' performance on these different conditions. Our expectation was that performance on tasks that rely on the same perceptual representations should be correlated across participants. We found that performance on harmonic and inharmonic conditions without a delay was highly correlated across participants, but with a delay this correlation was substantially lower. We observed the opposite pattern for the harmonic and interleaved harmonic conditions, the latter of which forces the listener to use a representation of the F0. For this pair, the correlation was lower without a delay than with a delay. Together, these findings suggest that listeners use different representations depending on the time delay between sounds. With no delay, listeners appear to rely on a high-fidelity but short-lasting representation of a sound spectrum. But with a delay, they transition to using a compact but enduring representation of the F0. The results demonstrate a form of abstraction within audition. Memory representations differ in format from representations used for online judgments. This might help explain the importance of F0-based pitch in music, where listeners must store notes over long periods of time in order to extract their relationships with other notes. To learn more about our results, you can read our paper, Time-Dependent Discrimination Advantages for Harmonic Sounds Suggest Efficient Coding for Memory.